Hopefully we won't lose halfway through. I got everything plugged in tightly. I'm not using that monitor. I'm using the other monitor. So it should be good. All right, so this is packet 6, class 7. If you're wondering, if you're watching the series here and you're wondering what happened to Wednesday's class, that was a review. That was a video key for test 4B for black and white. So you are in sequence here. This is class 7. We did some stargazing today, meaning I went around and checked papers. This really only pertains to Ben, but I went ahead and gave stamps today, but Ben can pick those up tomorrow. For you all, for the virtual kids, you're going to make up for all those stamps by submitting 6-1. We're not ready yet. I don't even think we'll be ready to submit it by Sunday because we're doing other things. So don't worry about it yet, but we'll be submitting that next week sometime for a bunch of points to try and make up for all the stamps. Meet table 4. We met table 4 today. I'm going to I'll go ahead and turn the camera off or turn the recording off. And if anybody agrees, let me pause the recording here in a second, but if anybody agrees, we'll meet you. You can turn your camera on and we all can say hello. So I'm going to pause recording. Okay, so we met a student and that was good. Now we're going to keep going. All right, so the first thing we're going to do today, we're going to do one of these on, so get out your 6.1. We're going to do one of these. We're doing number 10. And I made them go to the board. And here's the hint. So as we go to the board, once we get going, I'll once again put it on pause, but to give you time so you're not rushed. But my hint before I send you quote to the board, which is you working on your paper, my hint is that you're going to have 4 forces there. I'll do it in pencil. 4 forces. What other hint? Direction of motions to the right. 2 of the forces we've not put on a free body yet. Or, yeah, of those 4. Okay, so that's with that. I'll let you try and draw it. And then if you think you're brave enough to try and write the equations, but it's brave to write the equations in pencil, but I think it's kind of dumb to do it in pen only because you'd have to mark through it. Let's put it this way. Only one group out of the 30 that went to the board, only one group got it totally right. So anyway, the first time through. So now I'm going to hit pause and let you, and if you're at home watching this, you should hit pause and try and do number 10. All right. So I gave them a freebie, MG, and now let's put the rest of them on there. We have buoyancy, and I'm just showing you what I see people do on the board today. At this time, it is a new one because the buoyancy here was of air, and this buoyancy is of water. So BW, buoyancy is always a straight up force, always like mg, guaranteed. Mg by definition points to the center of the earth. Buoyancy by definition is always opposite mg. It has to be. Force of lift, not true. Normal force, not true. But buoyancy, guaranteed straight up. Now, this looks like, and this is what some people did on the board, they're trying to be good students, and they did that. Okay, we'll see if that's a problem. Then we write the force of pull like that. Force of pull. But I'm going to sophisticate this a little bit. This is actually a tension force. And tensile forces, this is a tensile force. Tensile force. And tensile forces come from ropes. Now, as you know, with a rope, you can pull. And so in class, I had a rope and I had a kid grab one end, I grabbed the other, and we pulled. And then we figured out the forces on that rope. So here on the next page. So if I have a point A and a point B, a person A, person B, whatever, let's say person A, person B, and then a rope in between them, a tight rope. This person, I'm pulling on B. And so there's a force like that. B is pulling on me. There's a force like that. These forces are equal and opposite. Those are called tensile forces. Tensile forces in cables, in ropes, can pretty much only pull. You cannot push somebody around with a rope. So these are pulling forces. This is tensile. This is T of B on A. This is T of A on B. And they are equal and opposite. But you go, wait a minute, they cancel then. Yes, because this is an example, by the way, of Newton's third law. If you consider A one body and B another body, that's Newton's third law, two bodies. If you consider the whole thing one body, this is all discussion Newton had. If you consider the whole thing one body, these become internal. And as Newton said, all internal forces cancel. So if you make it one body, if you make it two bodies, they don't. But if you make it one body, these two forces cancel. Tensile forces, internal tensile forces cancel, which is going to become big in June, because in June we're going to do these complex pulley systems, where we have like let's say we have a rope that goes around here and then comes back around here, goes up here, comes around, and then pulls. This is the pulley system. And then it pulls the whole pulley system. Here's these two are combined. These two are combined. And then we have, I didn't do this in class. And then we have some kind of mass here. Say we have 10 pounds. We're trying to lift. And I pull up on that rope. All of these become the tensile forces, T, 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 T. And you add up the number of ropes that are supporting and blah, blah, blah. And this is a pulley system, which it's also a machine. So tensile forces, when we get to pulleys, now unfortunately be June, will become really important. They'll dominate our conversations for a couple of sessions. Preview. Okay. So there's that tensile, because it is a rope, there's that tensile force, and that's 35 degrees. And then we have water drag, the new one, water drag. And so many groups did this. And you may have done this yourself. If you did, do not feel bad. That's wrong. But what's wrong with it? Oh, and by the way, the direction of motion is this way. It's being pulled horizontally along the water. So why does that make that? Say it again.
Isn't water drag always horizontal?
Not always horizontal, but it's always what?
Perpendicular?
It's not perpendicular. Force of lift is always perpendicular to direction of motion. If there's any lift involved. But drag always, someone complete my sentence. Drag always, nope. Okay. It's a little quiet today. Drag always opposes motion. And this boat is not moving up out of the water, it's moving through the water. And so your RA should be this direction. Like I say, don't feel bad. Only a couple of groups got that today. And then when I kind of settled, then everybody got it. But before, only a couple of groups got that. Only one group got this thing totally right. They got some extra stuff, extra bonus. So that's RW. And that is still wrong. That's pretty good, but what's wrong with my drawing now? Still something drastically wrong.
The buoyancy of water or whatever is
Yes.
too big.
Okay, thank you. It's too big. Thank you, Ben. Good to have Ben here. And so the buoyancy of water is smaller. And Ben knew that because you're getting some upward pull from the tensile force from the rope. So the ropes it's not pulling the boat out of the water, but it's reducing the amount that the boat is in the water. There's something called Archimedes Principle, that if maybe you learned that, supposed to, we did a lab. We wrote a lab for like 8th grade to do that, but I don't know if you guys ever still do it. But it's where a submerged body or a body that's floating in water always displaces a like if the boat weighs 50 pounds, it will displace 50 pounds of water. That's called drafting. Like a sailboat has a lot of the sailboats are under the water, right? Icebergs, most of them are under the water because they're displacing. More on that later, but actually we'll get to buoyancy. We'll talk about that more later. But because they're displacing an equal amount of water equal to their weight. Okay, I'll take that off there too. So now that looks better. Okay, now I could live with that. Now, did I ever tell you that a vector at an angle is the hypotenuse of a right triangle? I don't know if I ever told you that. Well, there it is. So this is your right triangle. And so this is actually T sub Y, and this is T sub X. So let me highlight that. There's my right triangle. T sub Y is, as you know, it's the opposite side. So it's T times sine. It'll always be this way. Y will be sine, X will be cosine. Sine 35 degrees. In June, there might be a case where we can't do that. But up through the end of school, it will be good. This is T cosine 35 degrees. I mean, if you're going to take AP Physics, you kind of need to hang out in June with this. You could watch the recordings, but you really need to have a live aspect to it. And we're going to be touring the OU physics building. We're going to be at the stadium running steps, and we're going to be in the park having a picnic. We'll be doing some things that you just can't watch on a videotape. Okay, so now we got to go down to the equations. Now, saying all that, I want you guys to write the equations now. If you haven't already, go ahead and write the equations. I'll give you a minute. Let me put it on pause. And okay, hold on, pause. And here we go. Let's see what you did. Just go with the X first. Okay, T cosine, I want TX, T cosine 35 degrees. I don't get any buoyancy. I don't get any weight, no mg, minus RW. I get all that one. Equals
0.
Thank you, Ben. Good to have Ben here. It equals 0. And Ben, why is that? I mean, Ben, it's moving in the X. It's moving with a speed of 10 knots, which is about 12 miles an hour. What do you mean 0?
I remember you were explaining it on the video, but I don't remember that.
It's not accelerating.
Yeah, there you go. Sophia came in and stole the point. Yeah, it's not accelerating in the X. It's MA. If you said MAX there and it's worth 10 points, I'll take off a point. I mean, you're not wrong. It is in theory equal to MAX, but you have to be more specific. The acceleration is 0. And so it helps you solve the problem, right? So it's equal to 0 is what I want there. It is moving, but it's not accelerating. Okay. And now we go to the Y. Okay. B buoyancy up. minus, I'll do on positive forces first, plus T sine 35 minus mg, and that one's also equal to 0. It's not even moving in the y direction. It's not levitating out of the water. It's not sinking into the water. So that's your equations. Okay. That's a lot. That's a lot of physics right there. Now I have this right here. So this will be on the next equation sheet, not on this one. I don't think you'll get this. You're not going to get this for the test next week. It kind of gives everything away. But here is a rocket. This is back when I did help videos on Vimeo. And I think Vimeo's the name of it, isn't it? Yeah. And then the district, I had like 75, almost 100 help videos on there. Then the district pulled the plug on it because somebody, I don't know, saw some boobies on somebody's Vimeo, and so they deemed the whole thing a porn site. Wasn't mine. We didn't find it on my channel, but they found it on somebody's channel. So they shut the whole thing down. Typical school system, abundance of caution, which basically I lost 100 help videos. So this old help video here is you good luck finding it. But it is on I have a Vimeo channel. I think it's like ASCII Physics or something. You can find it. And some of those I've moved over to YouTube, but some I haven't. Okay, anyway, so that might be on YouTube somewhere. I think it is. That's the thrust of a rocket. And there's the equations for that. And then today we just did this one. We did one like it. We said 35 degrees. That's 30 degrees. And notice I used FP. Today we went a little more sophisticated. Hold on a second. Okay, fine. So I said T today as intention. Okay. Good. Let's keep going. Now, here's the game I'm working on. I found this morning, I finally found it. There's a whole box. There's a whole box here full of my arrows. Can you see them? Let me, hold on a minute. Stop the sharing here for a second. So a whole box full of arrows that I had a student make me a couple of years ago. And I've spray painted these things. Some are black, some are white. I got some brown ones, red ones, all kinds of different colors. Okay, so we're gonna play a game in class with these arrows, a little puzzle building. And go back to the share. And the idea is to look at systems of forces. There. So the question for this one is, this is from last year. We played this game. I'm trying to work on the rules. I didn't like the rules last year or 2 years ago, because last year we couldn't because of COVID. 2 years ago. What's the relationship between the top set of arrows and the bottom set of arrows?
It's head to tail.
Top set of arrows is head to tail. Bottom set of arrows are the same arrows, only they are in a free body. So this is head to tail up here. Head to tail. Head to tail. And down here, it's the same thing, but this time in a free body diagram. But it's the same situation. What does the top set of arrows have that the bottom set of arrows don't have? Now, Sophia.
Summation of forces.
Okay, so Sophia and Ben are dominating, but I need to hear from Bennett. I need to hear from Io. I need to hear from Rose. You know what I'm saying? I got to hear from other people. Anyway, so say it again. Sophia, I interrupted you.
Summation of forces.
Right. So the top set of the free body diagram has this summation of forces arrow. which you need. It's telling me that's telling me the direction the whole thing's going to accelerate in. Normally you do not put, you don't put a summation of forces vector. You always do in a head to tail. You don't in a free body. So you can match these up. Like if I color this in, that's probably a poor choice. Hold on. Let me go purple, maybe green. So if I go, no. Let's go purple. If I go purple, that guy matches up with that guy. See, they're all there. And one more, just because it's fun. That guy, yellow guy, matches up with that guy. See, so they're all there. So the name of the game is you got to start with you got to start with, maybe I'll have them start with the free body, and they got to come there, show me using head to tail which way it's going to go. What's going to be the summation of force? Which way would this whole thing go? Because if I look at this, just looking at that, and I say, okay, which direction will it go? I kind of think it's going to go to the southwest, a little south of west, but I can't tell you the length or anything. And that's why this comes in handy, where now I know exactly what way it's going to go, and I know how fast or much acceleration there'll be. See what I'm saying? So another way in which head to tail is superior to free body. But the problem with head to tail is you can't put them into components, and you can't do the sines, cosines. You could, but it'd be a little harder. So think of it, there's a game coming up in the next day or two. We'll play in class, and maybe I'll try and find a way to show you what we're doing. Yesterday we derived, this is a thrust equation. We derived this yesterday. We got that. We did that derivation there. And then we did the homework. You're supposed to, if you're keeping up, you've done 1 through 4 on 6.2. The homework tonight, we did 5 together yesterday. The homework tonight is 6, 7, 8, 9. 4 more. The reason I can get away with assigning 4 problems is they're all like 1 or 2 steps, like boom, boom, boom. So keep up, do 6, 7, 8, 9. It won't take you but probably 10, 15 minutes to knock all 4 of them out. If you're taking longer than that, you're missing the shortcuts. Okay, so let's go on. Now, I want to spend the last little bit of time talking about hydrogen bonding and golf balls and stuff. Okay, so I don't know if we formally talked about this. I may have shown you the picture. This is a girl coming out of the water. It's not Aqua Girl. There's nothing fancy about her. This, in fact, you could get the same picture of you coming out of the water this summer, say at the municipal pool. If you're filming, it helps if you can go about 500 frames a second. But even at 30 frames a second, you can probably catch it at the right time. Everybody has this is surface tension, right? Which water has hydrogen bonding. So it's got it. And we went through the whole details in third hour. I don't have time to do that here. It's more AP chemistry stuff with dipole bonds. If you're in AP chemistry, Miranda would appreciate this. Dipole bonding, skewing of electronegativity, skewing of electrons towards the oxygen away from the hydrogen, lone pairs, all that kind of stuff. That goes into it, but that's called hydrogen bonding. And so there's a lot of hydrogen bonding in the water, and that's causing this tension, this surface tension. But the point is, we don't care about that really. The point is that the water adheres to the surface of the girl, just like it adhered to you. So looking at this, and I'll put that on the screenshots, but looking at this even from air does the same thing. This is the top of an airplane wing with air flowing over the top. And so if you do a cross section of anything, and I do like razor blades and all these real smooth surfaces you think are really smooth. And when you look at them you go 1,000 times, magnification, that razor blade actually looks more like this. It's rough, like a mountains range. So here's the smooth airplane wing. And remember we talked about them putting artificial shark skin into paint because it's going to help the drag on the wing. Well, this is why it helps. air, as it's going over the top, just like that water that attached to that girl, air goes over the top, kind of attaches itself and does little eddy currents. These little black dots, this is like it's air, right? So this could be let's go yellow. This could be like O2. This one could be an N2. Okay, these little diatomic molecules. And so they're all in there. It could be argon or carbon dioxide, but they're all in there and they're getting caught up in the surface, these little eddy currents. It's just like water in a stream. And that actually, the more that clings to the surface, this is counterintuitive, the more that air clings to the surface of that object, the less drag. You would think it would be the more drag, right? But it's the less drag on that plane. So they try and make surfaces not necessarily rough, but situated so that, and I'll show you how they do it, situated to show that air tends to hang around the surface more than laminar flow, like that laminar flow there. So here we go. Here's what I'm talking about. And we talked about this, I think the other day we did that, but here's a 1970s experiment. This is a bowling ball. Let's look at this one first. This is a bowling ball being dropped through water. And you can see where the water leaves the bowling ball, okay? Right along here, this is the zone of separation where that water no longer attaches itself to the bowling ball. It's because this is a smooth, this is a smooth bowling ball, okay? Then when they took that bowling ball and they roughed it up with sandpaper, some kind of a, they ran a sander over the daggone thing and made it all rough. And then this is considered a rough bowling ball. And then look what happened to the separation. The separation point moved from here back to here. You go, well, big deal. That makes a smaller, what's called the wake zone. That makes a smaller wake zone. Like if you guys have ever been on a boat and you think you're better than me, then you've been on a boat, then behind the boat is a wake zone. Okay. In front of the boat, you get through kind of a laminar flow of the lake, but behind them it's all turbid. Well, that wake zone puts a lower pressure. That's why I have that big L there. That puts a lower pressure on the object. In this case, it's a bowling ball falling through water, but it could also be a bowling ball falling through air because air acts like a fluid when things move through it. So if you have a big difference between this low pressure zone and the high pressure zone, that is drag, much drag, big drag. So big drag there. If the pressure is not as great, the difference, then that is a low drag, a lower drag. Because in this situation, you have less wake zone, which means less lower pressure. And so the difference between the high pressure, low pressure is less, therefore less drag or low drag. So who cares? Well, industry cares big time. Airline industry, golfing, tennis, pickleball, all of these look, here's for instance a golf ball versus a smooth ball. Golf ball has a smaller wake zone. Now in class, we watched a video about golf balls, and I will put that, it's a pretty good video. It's put out by the U.S. Golfing Association. So it's not made by physicists, so they speak in terms that make sense, but they don't shy away from the physics. So golf ball, putting these little divots in there, these little dimples they call them, allows, and the video does a real good job of showing this, allows those particles, like right here, allows those particles to stick around more and hang on to the surface more, which then the separation points gets moved back. And that's what I was showing you. I don't know when I showed you this, but here's a smooth golf ball. Here's a dimpled golf ball. and it goes to the history of it. They came across this serendipitously, meaning it's by accident. They used to play golf with smooth golf balls, and then they noticed that as the more they played, the golf ball got roughed up. It would go further when they drove it. And so I don't know whether it was the Scottish or whoever, but they said, hey, let's put these dimples in these balls. And then so the more dimples the ball has, the further it goes. So people cheat at golf. The typical, I think a standard golf ball's got, somebody can look this up, 331 or something like that dimples. And that's like PGA, that's what you have to have. And there's a certain number, I think it's in the 300 range. But some cheaters at golf put up to 420. You can put, and that makes the ball go further. One of the, they actually caught Trump on this. He's one of the main cheaters in golf, and his golf ball has a lot more. Now, it's not like it's illegal. If you're out there on the weekend duffing around, sure. I mean, go ahead and, you can impress your friends by having, keep it quiet if you want, but when you drive your ball, it'll go further because it has more dimples. It's because the air hangs on to that ball longer and has a smaller wake zone. You see what I'm saying? So there's all this stuff. You can do all this very interesting computer graphics from wind tunnels. And this is looking at wind direction and those turbidity currents. And this wake zone back here is pretty big. That's a problem because now you have this huge area of low pressure back here. That's like on a weather map. That's a low pressure zone. And then in front of it, relatively speaking, then that is a high pressure zone, and that's going to have lots of drag. Okay, that's not good. I mean, maybe it is what you want. I mean, in pickleball, you don't want you want to make a small court, right? So you can make more money. And so because you can have a smaller court, you can have more courts in a amount of acreage. So you want the daggone pickleball not to go very far. Ping pong. You don't want a ping pong ball to have dimples in it because you don't want to make the ping pong table bigger. Here's a tennis ball, and this is a tennis ball that is not a good tennis ball. Now it's rotating and that changes it a little bit, but this has a huge, look at this back here. This is a huge wake zone behind that tennis ball. So this is not going to go very far. The fuzzier the more fuzz on a tennis ball, the more that separation comes back here. And then you have a smaller wake zone, and therefore the ball goes further. And if you play tennis much, you know this. Good tennis balls, brand new, you open up that can, it smells so good. I love the smell of an open can of tennis balls. Reminds me of my youth. But those balls go a long ways. And then as a month or two goes by, you got to throw them out because they lose their hair. Okay. Anything else we talked about? Oh, then the next thing we did was we watched the golf video. So we don't have time to watch the golf video, but I will put it in the comments. It's a 4-minute golf video. It's pretty good. Okay. So stop the sharing. Hopefully the sound, it wasn't a waste of, my wife just saw this and scoffed at me because I'm, wasting money, but not wasting money. This is like, honey, we're going to make money.
It does sound better.
Thank you. There, I'm going to tell her that. I'm going to tell her that when she gets home, that unsolicited, a student said, Bennett said that sounds better. So thank you. All right. I think we're done. We're about at 2:00 tomorrow, Friday. Thank goodness. We're going to continue on. We're going to continue on that one sheet and 6-2. Stay up with us now. Do 6, 7, 8, and 9 on 6-2. We'll probably wrap up 6-2 tomorrow. We'll get another one done on 6. We may start 6-3. I don't know if, hey, you know what? We're not going to get to 6:15. I didn't think we would. But what we don't get to, we'll just push off to June, and then we'll add some more stuff. So, yeah. All right. So everybody can go. You guys are free to go. If you want to stick around and ask a question, I will answer it.
Hey, Mr. Askey, what was
Yep.
the secret word thing on your Vimeo?
What's the what?
The secret word
Oh, yeah. We
that
used to
you
always,
used to do?
yeah, we used to always do secret words like to see if the kids actually went to the watch the Vimeo or to what that I'd hide a secret word in there. And so then when they put the secret word on a test, they got like bonus. Yeah, I stopped doing that. That's a good one.
Oh, dang. Yeah,
should
there's 2 channels.
I should bring that back, that secret word.
Ah,
Yeah. Okay, Ben. You be there tomorrow?
yeah, I should be.
Okay, good. Well, if not, just come by. I enjoyed having you here. So either way,
All right.
we'll
See ya.
talk to you later. All right, bye-bye.